Good morning. So today is all about logical shifts. We want to be able to perform a logical shift to the left and a logical shift to the right. We want lots of practice on it. They're very similar to arithmetic shifts, but they are simpler. So, two types of shifts that we've got. We'll deal with arithmetic shifts in our next theory lesson. It's logical shifts today. The big difference is logical shifts are easier, but they only work with positive numbers. Arithmetic shifts don't work with negative numbers. No, sorry, try that again. Logical shifts don't work with negative numbers. Arithmetic shifts do work with negative numbers. So if you have a binary number and you shift that binary number across to the left, it's the same mathematical operation as what? So yeah, if you shift to the left, it's doubled. If you shift to the right, it's halved. Because if you remember, each bit has a bit value. The least significant bit is on the right, that's worth 1. The most significant bit is on the left, that's worth 128. You only have to deal with 8-bit binary at GCSE. So if each bit doubles in value as you move to the left, it makes sense that if you shift everything to the left, it's worth twice as much. And then just to prove it, if you have this, and let's double check that it is 23, 1 plus 2 plus 4 plus 16 is 23. If you shift them all across to the right, well, it's almost half. So yeah, this has been rounded down. Half of 23 is 11 and a half. In maths, you'd round that, wouldn't you, to 12? But this isn't maths, this is computing. We always round it down, and we ignore that bit. It's just disappeared, it's gone. That one has shifted right, and we've lost it. On the left-hand side, we've padded it in with a 0. Let's go back and see what happened over here. We've shifted everything left, and we've put in an extra 0 on here. That's it, really, for logical shifting. It's quite nice and simple. So, in P8, if we have a denary value before the shift, we need to first of all work out what that is in binary. So I want you to use your revision notebooks. I'll let you open this up and then we'll go through this on paper first. Okay, so let's go through this first example. We want to do 11 and it should be shifted left 1 position. So that means we're going to need to convert it to binary first. So let's put today's date, that is the 2nd of November. This is a logical shift. And we want to go 11 into binary. I know you can probably do this in your heads, but I want to practice the exam technique. You always write down the bit values first. I'm going to run out of space. Just about made it. Now, how do we make 11? You can think which of these values we need to add together, or we can do it the long way and think, do I need 128? Nope. Do I need 64? Nope. Do I need 32? Nope. At this point, I do need 8. And if I have 8, I've only got 3 left. So 4's too big. I'm going to need 2. I've only got 1 left. That should be 11. That's our first step. That's a recap of last half term. There's nothing new there. Our question asks us to do 1 shift left of 1 position. So that means every bit gets moved across to become more significant. That one disappears, goodbye, and a 0 gets shifted in. So that 0 appears here, that 1 appears here, it's now worth 2, that 2 is now worth 4, that 0 is still worth 0, but it would be worth 8 if it was a 1, and we keep shifting them across.
Even if it goes past.
If you had a 1 over here, it's gone, it's disappeared, it's lost. And that might mean that you've got an overflow. So any number bigger than 128, if you have a logical shift to the left, you're going to have an overflow and the result will not be double anymore. You will only double it if a 1 doesn't disappear off to the left. So that is our answer here. Binary pattern before the shift. That was our this value before the shift, so that's 1, 2, 3, 4, 1, 0, 1, 1. Binary pattern after the shift, well, it's exactly the same, except for 2 changes. We've lost a bit from the left, we've gained a 0 on the right. And we should be able to guess what this is. We hope it's double. So it should be 22. Let's prove it. Okay. We don't have a 1. We do have a 2. We do have a 4. We do have a 16. We add them all together. 16 plus 4 is 20, plus 2 is 22. It works. It actually works. That's what you need to do for activity 1, please. Let's go through activity 2. This time we've got the same numbers, or mostly the same numbers, and we want to shift to the right. So if we start with 11, we work out what that is. 1, 2, 4, 8, 16, 32, 64, 128. To get 11, we're going to need 8 plus 2 plus 1. And we're shifting to the right. I'm going to say logical shift 1 space to the right. That means that bit is lost. It's gone. I've got this bit, that bit, and all the rest are zeros, because in a logical shift you always fill the spaces with zeros. So if we had 11 and we've logical shift 1 space to the right, that's the same as dividing by 2 but rounding down, so we're expecting to have 5. 4 plus 1 is 5. It worked. That's what we do here. So how do we do it? We need to write down the binary value of 11. 128, 64, 32, 16, 8, 4, 2, 1. Shift it to the right. So it's the same number. We lose a bit on the right. We gain a 0 on the left. What's the value? It's a 5. So let's go through this one here. We've got the value before the shift, and we want to go a logical shift to the right 4 spaces. That means that 1, 2, 3, 4 bits are lost. They've gone. And it means that you've got 4 zeros padded in on the left. This activity doesn't ask us to work it out in denary. We could if we want, but it doesn't ask us to. Have we lost any precision? Yes. If there's ever been any 1s that have been shifted off, we've lost precision. Out of interest, I am going to put in here what these are. That's 5. So we've worked out the denary value of this binary number. If we're logically shifting right 4 times, that is the same as dividing by 2, dividing by 2, dividing by 2, divided by 2, which means dividing by 2 to the power 4. So 2, 4, 8, 16. So if we do 94 divided by 16, we get 5 point something. I know it's closer to 6, but it's not a maths lesson. We've lost the zeros. We're not rounding, we've lost them. They've been truncated, they've been lost. So it's just 5. So when you've saved your Word document, can you upload it to Half Term 2 Data 2, please?